Welcome everyone. I'm Ira Feldman. I'm the Executive Director of MEPTEC, and I welcome you to today's MEPTEC IMAPS Semiconductor Industry Speakers Series webinar. Thank you for joining us. Good morning, good afternoon, good evening, wherever you are in the world. Thank you for joining us. Upcoming Semiconductor Industry Speaker Series, we have presentations twice a month, booked out to the end of the year. October 28th, we have Chan Ji Xiling talking about co-packaged optical I/O. November 11th, Tim Orsley from Corning talking about ribbon aluminate laminates for advanced packaging applications. November 25th, we have David Keelet from Intel talking about chiplet technology, which his presentation will probably dovetail pretty well with what Bapi is talking about today. December 9th, we have Sandeep Razdan from Cisco. And on December 23rd, we will have a special gathering for the end of the year. So look forward to seeing people at these upcoming Semiconductor Industry Speakers Series presentations. A little bit about MEPTEC. MEPTEC is a membership-based organization, and so we appreciate people who renew or join. You can do that through the website, and we also have corporate sponsorship at varying levels. If you have questions about joining or sponsoring, please contact Betty Cooper, bcooper@meptec.org. And just a reminder, it is your membership and sponsorships that help us put on a lot of varied programming, including these free webinars. So we thank you for your support. So today's presentation is an introduction to the Open Domain Specific Architecture by Bapi Vinnakota. Bapi is a system architect with Broadcom. The other hat he wears, which may sometimes swamp him, is he's leading the Open Domain Specific Architecture subproject of the Open Compute Project, and he will discuss this in greater detail. And I think this is a really interesting topic, and the importance to packaging and test and design is that this will drive future requirements in those areas. And he's previously taught at multiple universities and has worked for several technology companies on working on application-specific processors. So with that, I will turn that the presentation over to Bapi.
Well, thanks for having me over. Thanks for your time. If you see me glancing to the left, it's to look at my extended monitor. So a couple of disclaimers before I start. Thanks for your time. If you have any questions, stop me at any time. I have zero attachment to the idea of getting through all the content. And I will also tell you where a lot of the content work depends on contributions from many, many people. And I will be happy to tell you where my knowledge stops, and happy to schedule a follow-on conversation with you.
And so related to that, everyone, if you would use the Q&A tool, I can ask the questions at the appropriate time in the presentation. So please use the Q&A tool, and we'll make the slides and recording available shortly after the event. So.
And thank you. And as Ira said, I'm at Broadcom. Broadcom's kind enough to let me continue working on the this OCP project, where, if you don't know about the OCP, it's an organization devoted to opening up the data center and hardware associated with the data center. There's a whole bunch of projects in this space. There's a tech summit coming up in a couple of weeks. You're welcome to register there. The OCP has projects in servers, in server storage, networking, in hardware management, etc. Some of which may be of interest to you. And I'm here. We have a group. We have a project in domain-specific architectures, which has a fairly decent active community of 30 plus. I'd say it's 35 plus companies right now. So the talk itself, what I'm going to do is first start with sort of a top-level overview, go through what the motivation is, and really give you an overview of our company, of the community, and then go down into some level of technical detail, not a whole lot. And really, I'd like to spend some time on really how you can participate part of the reason I was sort of pretty excited when Ira asked if I could speak was because we're planning on building a few test chips, and we could definitely use packaging help for the test chips. This isn't a really detailed technical deep dive. What I have is through the slides, you'll see pointers to the source material for the slide. So one of the things that we've done well as a group is produce an enormous amount of technical content, and you'll have pointers through the talk and at the end of the talk as well. So chiplets are receiving more attention. It's one of my hobbies. Every 3-4 months, I go off and just say chiplets and see what pops up on Google News. And I'm very excited to see you've got Dave Kellett coming up in 2 weeks. Make sure you don't listen to anything he says. But jokes aside, I'm really excited you have Dave Kellett. They did a lot to open up this ecosystem along with a DARPA project. So I'm very happy to see the packaging community getting more engaged with open chiplet efforts. And really what this boils down to is there's that some sense, which all of you are familiar with, so it's one of the big reasons I'm sort of sliding through this material, is that really scaling as we know it is being hampered by a variety of factors. Clock frequency scaling has stopped. There's some sense that single-threaded performance is stalled. So really you're growing by core count, and how much can you extract from parallelism? And the second sort of interesting artifact, which I found some data for, is that most foundries are now leaving sort of more mature nodes open for use for far longer. So the cost of masks, the cost of tape outs, et cetera, are presumably lower in these more mature nodes. So the second interesting trend that's sort of paralleling this trend of the slowdown in Moore's law growth and more mature nodes being available is this growing interest in domain-specific accelerators. Because sort of the natural corollary of single-threaded performance stalling out, power limits and chip physical limits maxing out the number of cores you can put on general-purpose silicon. The next sort of natural thing is, okay, we have workloads which are growing faster than the CPUs can handle, so we need domain-specific accelerators. And you've seen this, you're really seeing this in 2 or 3 different places. One is obviously at the data center, where you've seen pretty much all the hyperscalers announce different accelerators for various applications, typically for learning, inferencing, video transcoding, compression. There's just a whole bunch of use cases for domain-specific accelerators. And you've also seen it in the development of system-level protocols, right? You've seen it in the development of CXL as a protocol to keep an accelerator coherent with the host CPU's memory. And in general, what I've noticed is these domain-specific accelerators tend to be produced in more mature nodes. There's a portion of them which gets produced in the most advanced node. There's other kinds of domain-specific accelerators which get produced probably 1 or 2 nodes behind the sort of leading cutting edge node. So when you put these two together, you kind of get
Sorry,
yes,
Bapi. With the domain-specific accelerators, are we likely to see these deployed beyond the hyperscale data center? Is there any use case where it might be an edge node or in a consumer product, or is these typically only going to be in the hyperscale?
So thank you. So it is. There are the 2 other places where you're seeing domain-specific accelerators are in the edge, and there's some sense that it's going to come through in automotive as well. And if you kind of look at most vendors are beginning to produce special purpose chips in automotive, and the other end is in the extreme small form factor products, IoT and wearables and mobile products, right? So those are places where you'll see domain-specific architectures, domain-specific silicon show up. So in some sense, we're using these as a reference to guide the decisions we make, not to say this is the only silicon we're targeting with our work. But think of this as a reference architecture, reference use case to guide the group's decision making. Does that make sense?
Yes, thank you.
So if you sort of glue it all together, and this is actually from a, so what you'll notice is in the slides, you'll notice like a little green box, and what that is a pointer to a the source material for the slide. And this particular slide I swiped from a gentleman named Dharmesh Jani at Facebook. He gave a talk at one of our workshops in Amsterdam at the ODSA workshop in Amsterdam last year when we were all still traveling. And what he sort of the idea is that Gordon Moore made two observations. One is the famous Moore's law, and the other observation is basically, hey, maybe you start building things as collection of die instead of a single monolithic die. And that basic observation has sort of gained more traction in the recent past, right? So really so you put all of these trends together, and you're sort of beginning to look at the idea of products based on chiplets. So instead of making a silicon product from a monolithic die, you are making it as a package collection of die, as a collection of multiple die in one package. And there are two or three motivations for this. One is you're disaggregating a large die for yield, or the second is you're trying to promote modular reuse, where you're reusing components. And this goes back to each kind of function being suited to a particular process node, being most economically manufactured at a particular process node. So there's been some consensus that analog circuitry really doesn't benefit from shrinking to the most advanced process nodes, as an example. So you want to pull those out into a more mature node to lower your costs, or memory typically is in a different process node from processor logic. And what happens when you do all this, so the reference paper in my mind is the CEO of AMD had a paper at IEDM in Vegas in 17, and talked about how they were making their CPUs as collections of chiplets. And you can trace a lot of work back in my mind, you can trace a lot of work back to that paper, and how maybe products were better made as chiplets than as monolithic die. And before AMD, it was Marvell sort of who started this idea of modular reuse across their product line. Now the catch is, once you have multiple die inside one package, you're going to need some interconnect between them. You need some kind of physical interconnect, and you need some kind of logical interconnect between the die, because they have to be first wired together, and then they have to share information. And today, the thing is, almost all multi-chiplet products use proprietary die-to-die interconnect. And what that means in practice is that they tend to be single vendor products. So the product designers made a conscious choice to split it into multiple die, and the same entity owns both sides of the interconnect. So given this increase in chiplets, so one of the things we did commission as a group is a market forecast by Omdia, and I'll let you dive into the details. But the basic bottom line message is chiplets are going to be an interesting market in the near term, and are going to be really a breakout market in the mid to long term. And there is a talk at a workshop we held at Facebook in December 2018. It was our last one before the lockdown, so it feels like we held it yesterday. It's almost 10 months ago. And that has a lot more market detail, and this slide is accepted from that talk. Let me pause here. So this is the preliminary overview material. Any questions, any thoughts questions I can answer or cover?
So is it at the end of your slides, you have the URL to the wiki that has all the presentations?
Yes, I do.
Okay.
Yes, I do. So our wiki it contains, we have calls weekly. So wiki contains recordings of the calls, and we usually have a whole bunch of speakers on various topics. It has presentations from all our workshops, and it has pointers to technical papers that we've written. And I have a pointer to the wiki at the end of in the last slide, or the third slide from the end.
Okay, great. And any specific questions from the audience, please, if so, use the Q&A tool. Let's proceed, and we'll see what comes in.
Sounds good. So our particular group is focus on this idea of chiplets and really saying, okay, can we build accelerators out of chiplets? And really, can we, but more importantly, can we build chip accelerators, which are a collection of chiplets with open interfaces? So you can mix and match chiplets from multiple vendors into one, integrate chiplets from multiple vendors into one package. So the picture on the right is an IBM Power 9 reimagined as a collection of chiplets. It's by, excuse me, right, Jeff Stukley and Josh Friedrich from a workshop we held at IBM about a year ago. And the picture on the left is another picture from DJ's talk, which really talks to the enormous range of domain-specific architectures that you're seeing at different hyperscalers and at the edge. Because just in neural networks, you're seeing an astonishing range from inferencing, learning, spiking, neuromorphic networks, you name it. And then in video acceleration as well, you're seeing a whole bunch of applications. So our group really splits its activity into three broad classes. The first one is the act of just defining an open interface. How do I define an open physical and logical interface for chiplets? And the second thing we try to do is this idea of reference designs. And the theory of thinking behind this is if we can make the work product of the group much easier to use with reference designs or even prototypes, that the interface will be more easily used. And the third thing, what we realized early on, but we really haven't made as much progress as I would have expected a year ago, is that early on there was a recognition that workflows and chiplet-based products needed to change. And our group has done a fairly decent job in my mind of identifying the problems. And I think we are looking to make a lot more progress on potential solutions, especially when you deal with multi-vendor products. You're dealing with issues of like, who owns the final yield, who owns product liability, how do die get transported, and what kind of information gets moved with die, etc. And the bottom two are where I'm really hoping that we can get more engagement and interaction with packaging and test people. So we've, as I've sort of alluded to, we've been in flight for about almost 2 years now. We started with a group of around 7 companies 2 years ago, roughly, and actually at the Linley conference. And in fact, the Linley conference this fall is all about domain-specific architectures, if I remember correctly. The agenda is kind of very domain-specific accelerator focused. And from sort of a starting group of around 7 companies, we've got sort of, interested participation from close to 100 companies. We've got active participation from about 30 to 35 companies, basically. And these companies are spread across the entire value chain, as it were. You've got IP vendors, semi vendors, people involved in the design of products. Then we've got tools and manufacturer and design and test vendors. And finally, we've also got some decent systems vendors and people who actually use the end users, etc. And that's one of the interesting things about chiplets is you really have a interplay between various factors. So one of the things we were looking at, we're doing a test workshop in about 2 weeks, 3 weeks in conjunction with the International Test Conference. And to me, one of the sort of really interesting things is that chiplet-based designs are a place where you have a solid interplay between packaging and test in a way that you may not in a monolithic device. So roughly our group's activities are split into multiple work streams. Each work stream is sort of focused on a particular aspect of the problem. So the PHY layer is really focused on sort of, cross-PHY analysis and building different kinds of adapters, and I'll get to that in more detail. We have something called a bunch of wires PHY, which is kind of a new die-to-die PHY developed by our group. And its aim is just to be sort of an easy to design, low cost PHY technology that can span multiple packaging technologies. Typically, when you look at any PHY technology, it's coupled to the way you package it. And say, for example, and I'll come to that in a bit. Then we have a group which may be kind of interesting to the people on the call, called the Chiplet Design Exchange. And the idea here is that if you're doing sort of a chiplet-based design, in addition to the die, there's a bunch of information about the die that has to travel with it. What kind of information needs to travel with the die about thermals, physicals, etc. And how does that work, basically? Then we have a business work stream led by a gentleman from NXP, which is now seeing a pickup in activity. We have two POC work groups, which I'd like to go into in a little bit more detail towards the end of the talk. Then we have another group really focused on the link layer, talks about the link layer is a key part of the die-to-die interface. Finally, we have a high performance open PHY led by a gentleman from Xilinx, which is really sort of a alternative or a much like the AIB, a very high performance interface derived from the HBM interface. And finally, we're just about to kick off a new end user group. And the idea this group will end up being a closed group just of end users, hyperscalers. And what they're going to do is really funnel their requirements into the ODSA, saying, this is the kind of functionality we're interested in. These are kind of bandwidths, packaging technologies, use cases, and hopefully that information filters through to the rest of the activities in the ODSA.
So Bapi, for those people who are more involved in packaging and test, would you define a PHY and what's in a PHY and what's not in a PHY?
Right. I will in three slides.
Okay.
I thank you for the reminder. Appreciate it. And I'm glad. So let me knock off the overview, and I do have a slide which captures that. So again, so we've roughly, the group has been fairly active across this. We'd love to have you participate more. This is sort of a rough layout. One of the things I really miss that the pandemic has really hurt us on is we met physically once a quarter at some company. We met at Global Foundries, Samsung, Intel, IBM, Facebook, and now we're sort of like, hanging out online permanently. And so that's been a problem. We are going to participate in a 3D and chiplet test workshop at the test conference. There is an OCP Tech Summit coming up if you're interested, and we've got like a POC that I'd really like to talk to you about. So this is kind of a rough overview of our group. If you want to participate, we meet Fridays 8 to 9 a.m. Online, and each work stream meets independently. The Friday meetings are recorded, but the work stream meetings are informal. If you'd like to join any work stream, pretty much everything we do is out in the open. You can sort of come and go at your convenience at any time. Okay, so what I'm going to do is going to transition into sort of a slightly more technical content. I'll again pause here to check if there are any questions. If there aren't, I will keep going. Okay. So this is one of the most surprising things to me that the community as a whole sort of figured out, has sort of settled in on two interesting use cases for chiplets. This particular slide I stole from an Intel engineer named Ramune Nagisetti, and this is her talk at our workshop in last March. And if you look, IBM, Jeff Stukley, and I'm forgetting the other gentleman's name. Anyway, he has a very similar breakdown of use cases. And if you kind of go through, I think we had a talk from a gentleman at Socionext, and it turned out they're looking at exactly the same use cases. And all this boils down to basically there's sort of two broad things that people look at. One is this idea of package level integration. So something's on a board and I want to squeeze it down into a package. And the second is this idea of die disaggregation. The idea is that I've got a large die, and because either I want to assemble it more quickly, I'm either going to break it down just to make a smaller die for yield, or I'm going to break it down into modular components that I can reuse. Why does this matter, what the use cases are? Because it kind of tells you what the protocols are with which you exchange logical information. So if it's a board, many of you may already know it's going to be PCI Express, maybe it's going to be NVMe, or it's going to be moving forward, there's a good chance it's going to be CXL. If it's a die that you're breaking up, it's going to be an on-die bus that you're going to use to exchange information. It's going to be an AXI bus from ARM, or it's going to be a Sci-Fi, or if Sci-Fi's architecture as it grows in popularity, the on-die Sci-Fi bus may be the mechanism with which you exchange information. So what the use cases tell you is what's the mechanism by which logical information is exchanged between the die in a package. Okay, and I'm just going to zoom right past this. There's a lovely slide by Elko Bergman from ASC. Don't know if he's online or...
Elko is online, so we can pull him in later if there's questions.
In this case, I really had to help him make the slide. So, but this Elko has a really nice talk, and I think it was a couple of months ago on our wiki, the range of packaging options that you have for these multi-chiplet packages. So come back to Ira's question of what a PHY is, basically, right? So now when you look at, this is a sort of a simplified view of a multiple chiplets in a package. And there are two problems you got to solve. Problem number one is, how do they physically get wired to one another, right? And that's typically they get physically wired to one another using a die-to-die PHY. So there are two broad choices, and I'll come to that in a second. Then once they're wired, you need some logic, interface logic with which you exchange information. And typically the protocols that you use to exchange information are either going to be those that you use for package aggregation, like PCIe, CXL, C6, or they're going to be protocols that you use on a die, like AXI or ARM CHI interface. Or TileLink is a new one from Sci-Fi, right? So RISC-V, thank you. That's the name I kept hunting for, RISC-V. So when it comes to PHY, so there are really two broad choices in the marketplace for PHYs. One broad choice is to take the design of an on-die bus and move it to off-die. So you tunnel tons and tons of wires between the die. And Dave Kellett is going to introduce you to the bus, the bus that Intel opened up called the Advanced Interface Bus. So I'll let him walk you through that. The second option is to take the kind of protocols you use for off-package, something like PCIe, and move it to on-die. So the off-package protocols typically tend to be serial protocols, which involve high-performance SerDes. And what you do is you move the same kind of SerDes protocol on package. And the idea here is that the reason you want a new PHY optimized for die-to-die communication is that you want its performance to not cost you a lot in power efficiency. So this turns out to be the magic figure, 0.5 picojoules per bit, right? Basically, if you look at something like PCIe, so the natural question is, why don't I just take PCIe and move it, use it between die? And PCIe has a power cost of anywhere between 8 to 10 picojoules per bit. And so what you're looking for is a dramatic reduction in power costs. Now, the next natural question is, why don't I just take a highly parallel on-die bus and move it off die? And that's a perfectly reasonable answer. Typically, what happens is that your packaging technology becomes more complex when you do that. You almost always need advanced packaging technologies, and again, so it boils down to a choice of how complex. This is one of the really interesting things in my mind in chiplet-based designs. Typically, factors that a designer typically considers way downstream have to be accounted for in the architecture. Because in my mind, if you choose bumps or micro bumps, it's going to figure out what your test coverage for known good die is. Are you able to use a regular tester? If you use regular bumps, you can probably test them inside the wafer. If you use micro bumps, do they have enough drive? Can you build a tester head? If you choose a highly parallel bus, you're committed to advanced technology like interposers or RDL. So one of the most interesting things about chiplets in my mind is that factors which normally don't get considered by an architect have to be modeled and accounted for early on in the design process. And one of the things we're trying to do is figure out if there is a way to actually do that. If there's a way to sort of say, model these as simple binary choices or quick choices that an architect can take into account in designing these products. So you say, I want a terabit per second between chiplets, and you say, well, your choices are, you can go for highly parallel buses, which means you're going to go interposes, and your product cost is going to be this, or if you can go for a serial PHY. So this is one area which is not well defined, but we're sort of trying to pay more attention to it within our group. We have something called an open mic where anybody with thoughts on it can come up and spend 5 minutes on the idea. And this is one topic in which we're really interested. How do you represent downstream components early on in a way that makes sense to a product architect?
So a question that happens in system design when you have multiple chips, if you have, let's say, a lot of I/O pins and you can't randomly reassign them, and you have two different parts and you have to do the interconnect between two different parts, you get into how many layers of printed circuit board routing you need to do the crossover, for example. And I'm assuming people don't want too many layers of metal on their interposer or their bridge. So how do you solve that?
So that is a really astute observation, and really what distinguishes die-to-die PHYs is their packaging cost. So many die-to-die PHYs make deliberate choices of what they're optimizing and what they're giving up in something else. So effectively, when you choose a die-to-die PHY, you're also choosing a packaging technology and the associated routing complexity. So it comes as a package deal, right? So typically, when you buy soft IP, when you buy an interface, you buy it as soft IP. But what you're really doing is you're buying the in-laws as well, effectively, right? I mean, you're buying a whole bunch of things at the same time, right? So really, each interface has, every interface is done. When you look at a spec, so if you look at the AIB spec that Dave Kellett will talk about, or if you look at the Open HBI spec or HBM, or if you, the bunch of wire spec that we're doing, everybody takes generates a first order estimate of routing complexity between two interfaces of the same kind. But if, let's say I have a chip with a bunch of wires interface and I needed to talk to an interface with an AIB, that's a discussion we're beginning, but there's no formulaic answer for that. There's no well thought out answer for that, right? So fundamentally, a lot comes down to two big things. If I'm a chip designer, system designer, I want to live and reuse the protocols I'm familiar with. I don't want to go out and go out and use a new protocol for my system. I want to use PCIe, CXL, C6, or AXI, or CHI, whatever it is that I'm using for that. But at the same time, we as a community want to give system designers the opportunity to try out multiple PHY technologies. We are not smart enough to declare one technology to be a winner. We're kind of saying, look, so what we're trying to do as a group is sort of set the rules of the road, as it were. So what we're saying is effectively, look, if you can define an abstraction layer between the PHYs and the transaction protocols, and the community agrees on those abstraction layers, then as long as your PHYs support this abstraction layer, you can carry today's transaction protocols on the die-to-die PHYs. You can use die-to-die PHYs as an underlay for these transaction protocols. That's basically been the thrust of our the way we've gone. And really, one of in my mind, I think the person who came up with this first was a gentleman named Brian Holden from a company called Candu, and he kind of said, hey, why don't we use the pipe interface from Intel as a mechanism to carry PCIe traffic? And as a group, it was a very nice generalization from there kind of say, look, we can use, if we define an abstraction interface, we can use that for every protocol out there. We can use it for AXI, we can use it for, we can use it for coherence protocols, you name it, basically. And so coincidentally, what Intel did very politely was define a second open interface called the Logic PHY interface, which they originally defined. The pipe interface was an interface they defined between PCIe PHYs and PCIe controllers. And the LPIF is kind of like a higher level version of the pipe interface. And so broadly, we as a group want to use both of these interfaces, the pipe for when we're carrying something like PCIe, and LPIF for a whole range of other applications. And the idea here is that as you go from left to right in the stack, I won't sort of go down the rabbit hole of walking through the stack in detail, but the basic intent of the stack is for us basically to take a existing off-the-shelf PCIe controller from a company that sells PCIe IP, like Synopsys or Cadence, and use it for die-to-die PHY applications as is with no changes. And the way we do that is that we tell a die-to-die PHY to spoof being a PCIe PHY, to pretend to the PCIe controller to interact with it the same way a PCIe PHY would in the data plane and in the control plane. And if you do that, now magically you can sort of take a system design, replace the PCIe PHYs with die-to-die PHYs, and dramatically cut power dissipation. And one of the big decisions we made early on was that we wanted this abstraction to be available to anyone, in the sense that we didn't want it to be just for the die-to-die PHYs that our group, or just for open die-to-die PHYs. So somebody with a proprietary die-to-die PHY, there are quite a few companies with proprietary PHYs, they're welcome to use this abstraction interface as well. We want to provide a guideline. So fundamentally, we want to be in the business of not deciding which technology is a winner, not deciding the right fit for the market, but just sort of laying out the rules of the road and trying to minimize the new things that we invent, and hopefully promote interoperation that way. So this is roughly as you go from left to right, your essentially designs become more chiplet aware. So right now at the left part of this stack, our plan is to go to companies which already have chips which are sold as standalone die and help them to convert those to chiplets. Just sort of say, look, you can take an existing die and convert it to a chiplet by replacing your long reach interface with a die-to-die interface, and you can carry all the protocols you're used to. And then as chiplets gain more market penetration, we'd have the ability to basically carry these protocols more efficiently. So coming back to, I'll walk you through what we're going to have available in the back half of this year. Excuse me, we're already in the back half, by Q4 of this year. And there are 2 or 3 things we're going to have available. The first thing we're going to do is we're going to have a fairly simple PHY. So remember how I said a PHY can either be a wide parallel bus, which goes off the die, or it can be a SerDes bus, which is more like an off-package bus. As you know, this is our attempt at having the cake and eating it too, basically, which is we're trying to make a PHY which works with multiple packaging technologies, is easy to design. So the basic trade-off you get is when you have a highly parallel PHY, it's easy to design. The circuitry is easy to design, but it's harder to package. When you have a serial PHY, like a serial die-to-die PHY, it's really hard to design, but much easier to package. And we're trying to split the difference and have a PHY which is reasonably easy to design and reasonably easy to package. That's our attempt at the bunch of wires PHY. And this PHY is developed completely in the open. It's developed by a consortium of about 8 companies. Marvell, I take part in that. We've got people from Facebook. We've got people from Keysight, a couple of from IR Labs and from Apex Technologies, and a couple of other companies where they're going to kill me when I don't remember the name. But we've got a fairly healthy consortium of experienced engineers doing this. But the basic idea is that we want a PHY which can work at regular C4 bumps, which can work with micro bumps and interposers and RDL technology. We want a PHY where if somebody is interested in putting in more effort, they can get higher performance per lane. If somebody is interested in spending more on packaging, they can get higher bandwidth at the edge. So what you see here in this are what are called sort of the beauty contrast metrics for a PHY. Essentially, how much power does it take per bit to move from die to die? And the other interesting thing is this is typically the one thing that everybody cares about is what's the beachfront performance? How many terabits can I squeeze in per mm, right? So if you because the die edge is a fairly precious quantity. And one of the things, going back to your question, is the bump maps. Actually, this PHY specifies a signal order. It doesn't specify bump maps. So the signal order leaving the PHY is specified so that you don't need more than 4 layers, 2 to 4 layers, depending on how you want to connect them. So if you're the PHY specification allows stacking up to 4 deep, and it's still there's still routing solutions which limit the number of routing layers between die. Right. So this spec is available at the GitHub repo. We've sort of developed it over a year and a half across various conferences and journal papers. We had presentations at last year's Hard Interconnect and this year's, and a publication on IEEE Micro. And the spec itself is completely in the open at GitHub for anybody who's interested in using this. Let's see. So what we're going to have hopefully by the Tech Summit is we're going to have a bunch of wires PHY, and we're going to have an adapter to carry regular PCIe traffic over a bunch of wires PHY. And the second thing we're going to do is we're going to have an adapter to carry AXI traffic over a bunch of wires PHY. So we will have 2 portions of the stack which basically capture the 2 most common use cases for chiplets, a fully specified stack. And we would like to make the transition to building prototypes for this, and which is where I hope to get some engagement from people in the audience, where in terms of either packaging POCs or test chip POCs. So the protocol to carry AXI traffic over a bunch of wires is something that was open sourced by NXP. The bunch of wires PHY is being developed by a group of people. The pipe adapter for the bunch of wires is also being developed by a group of people from a company called AnalogX, and AnalogX, IBM, SocionX, and I participate in that as well. So really, we should have a fully developed die-to-die physical and logical interface for two popular use cases, right? So this is what we're going to do by 2020. Any questions, or should I just keep moving?
No questions at the moment. So let's keep going, and we've got about 10 minutes left.
Sure. So I'll swing into a couple of things which I'm hoping are more directly related to what you're doing. The CDX group, they discussed this at DAC. They've got some thoughts on power modeling. They worked on it with a couple of other open organizations. The idea is, how do I build power models for chips so that very early on in the development process, I can sort of figure out what my power constraints are in a package and what the peak participation is, how can I sequence things, etc. And I'm happy to send you more information on this. The main thing here for us is this comes back to the idea that when you are developing a die, normally if you would just sell the package part, if you're selling the die for use in a package part, you'll have to also ship some metadata about the die. You'll have to ship information about its power profile. You'll have to ship information about the interfaces and the pin order, etc. And we're really trying to figure out, what is the best way to share that information while still preserving IP rights and while still preserving the information that you want to keep secure. Because this is typically not stuff that a ASIC vendor releases into the market. So the next thing, we sort of put out a paper about this with Teradyne and co-authors from NVIDIA, Facebook, and Advantest, was this idea that, look, if you're going to do multi-chiplet workflow, you've got this known good die problem. If you've seen this, you'll see that this is one of Phil Nye's slides. I don't know whether, I think we credited him somewhere in there. Yeah. So this is one of his, there's a huge database slide. And except that, we think now this is going to extend across vendors. If you want to, so a downstream, when you produce a die, the thinking is that you're now going to may have to meet specific yield requests from a downstream customer. So not everybody gets the same yield. Different customers get different yield depending on whether they're willing to pay more, that you're going to have to move tests up the flow in some fashion. And again, in some sense, some data has to move about the part. And we think that this is a big problem, the act of moving data with a die. We just don't have any solutions or answers yet, but there's general recognition that it's a problem. So finally, I want to make a transition into what we built. This is a system design board that we built as a group. I'm actually astonished by the effort that the groups put in. It's a collaborative design effort across many, many companies. There's a gentleman, engineer from Cisco, who came up with this idea of, why don't I give you a system level design which allows you to explore chiplet architectures. So I'm going to give you a baseboard which kind of mimics a substrate, and that baseboard provides power, test, management interfaces to daughter cards that act as chiplets. So we call the daughter cards PCB chiplets. So we're integrating parts from NXP, Broadcom, Lattice, and Samsung into this board. And the idea is that, if you later today, sometime later in this year, somebody comes up with a bright idea for an accelerator, they can reuse two of these three boards. So they can still keep the networking part from Broadcom. Maybe they say, look, I'll insert the management later. I'm going to put my accelerator in there. And I'm going to reuse the general purpose CPU from NXP. Or if somebody comes up and says, look, I want to replace the ARM CPU with a RISC-V CPU, the only thing that they have to design is the chiplet daughter card, right? So this POC will be hosted and available at Supermicro. The design's in the fab right now. It should be back by the end of the month. And hopefully by November or December, Supermicro has been kind enough to host it in their site. And we want to provide access to anybody who wants to use this to develop SoCs.
So a question on that, from the audience. What kind of challenges are being faced while you're doing the physical implementation of a board, integrating these multiple chiplets or these daughter cards in this case, but they're acting as chiplets?
It's funny you should ask that. We literally have a presentation at the Tech Summit just about this, almost entirely accidentally. It turns out to be like, really mundane things turn out to be hard, right? Each part typically may have its own memory interface. How do you sequence power to these guys? How many different power supply rails do you get? How do you get everybody aligned on a common management bus? How do you sequence operation? How do you do presence detection? How do you automatically know whether the board exists? So there's a whole bunch of I'd say just mundane logistical problems in my mind that package designers face, that if you could somehow standardize those, that there would be a lot of value in making design turnaround much, much faster. So one of the interesting things this has highlighted to us is how many service and management problems somebody designing a pitchlet, how many service and management problems we have to resolve so that all you need to do is design a pitchlet and not the rest of the board. Data gets fed to you. You have access to a general purpose CPU. You have access to an x86 host, that you've got all of these things, and just say, all you need to do is design your unique function.
So sort of like people who are designing IP blocks and semiconductors, they don't worry about a lot of the overhead functionings.
Exactly. That's a very, very, very elegant way of putting it. That's exactly right. And now we have sort of a board version of that.
Got it. Okay, thank you.
And what we'd like to do is that the specs are open. So if you have a company who says, hey, I want to reuse. So, typically it turns out, and the reason we chose these parts, if I'm going to spend a couple of minutes, is basically almost every accelerator needs to fetch some data from the network, needs to talk to a host, needs some general purpose compute next to it. And really what we're doing is we're saying, well, we're going to give you all those pieces. We're going to feed data to you through the NIC. We're going to give you a general purpose CPU. And all you need to do is change change that accelerator portion. So that you can focus on designing your IP. So what we'd like to do going forward is really build more. One of the big things where I'm hoping I've intercepted this group at the right time. I don't know if Farhan's online. He's been very patient. So we're really beginning to build a die-to-die test chip, where we'd like to build a die-to-die test chip for the bow interface to prove it out. And we are considering two options, one with laminate packaging and one with more advanced packaging. And one of the struggles I have is, I appreciate some advice from anybody online. So people come to us and say, all right, I've built this thing with like a million wires going through the package and your stuff is just not complex enough. And when we build test chips, they tend to be proof points, which are inherently less complex than products. But when we generate these proof points, we think that we can transition to real world products fairly quickly after that. So we really would love active packaging participation in these test chips. The second test chip we really want to do is really take some design on this board and convert it to a integrated package using some kind of a workflow, just to define the workflow. And the struggle we face there, and that's the other thing I forgot about, which is that companies don't want to give you this information. They don't want to tell you what the die size is. They don't want to tell you what their thermal footprint is. And we really had to fight. That really is a bigger blocker. Just how do you share information? If the NDA is the only mechanism, then you're really one of the biggest pain points we faced. And if there's a way, is an N-way NDA. Like, if there are N parties, just N people signing mutual NDAs was a big pain point. And we still don't have a clean solution to that. And sometimes we just throw up our hand and forget it. We'll just do everything in the open. Much easier. You tell us, don't tell us anything you don't think you need it, that you need to be a secret. So this is the promise slide with pointers to everything. All our specs are online. All you have to do is ask for access. The group has done a phenomenal job of publishing material, and in refereed conferences and journals that go through academic scrutiny and peer review. In some sense, it's good to have that kind of critical feedback so we can stand up to that. The wiki has tons and tons of talks by lots of people. If you're interested in speaking to the group, please, by all means, come on over. We'd love to have you. And Ira, I forgot to put a date for the Tech Summit. I knew I forgot something important. We have these are the sessions we have at the upcoming Tech Summit. It's the week of November 9th, organized around Veterans Day. So you can register at the OCP website. I will send Ira the link, the Open Compute Project's website, the Tech Summit. I think the registration fee is about $100. We've got talks on the interface, on reference designs, and really we could use some help on workflows. I think that's really where we could use a lot of help. And this is my finally my shameless plug for, help us. We need your help. We could use anybody who wants to. You could use our stuff. You can review stuff. There are tons of ways in which we'd love to work with you. So that's basically it.
Wow, thank you, Bapi. Are there any questions that? Okay. So another question is, with the news with NVIDIA acquiring ARM, will this change what you're doing in ODSA or in development?
I don't have a good answer for that. I think we think it's fundamentally useful to have open interfaces just for that. There's just like, there's been a surge of interest in open CPU instruction sets and open other open architectures. We think it's useful to have an open interface, so that you can actually integrate products from multiple vendors. That you at least have the option to integrate packets from multiple vendors.
Okay. So multiple options and probably multiple architectures. So you could support an Intel processor, a RISC processor, things like that.
Exactly.
Equally well.
So,
okay.
Exactly. So you're at least leaving you're creating the space for interoperation of components from multiple vendors. And if you don't have an open technical definition, then that's nearly impossible. I don't know that we're a sufficient condition, but I'm pretty confident we're a necessary condition for that to happen.
Okay. Good. Okay. Any other questions? Oh, why don't we do this? Let me.
Oh,
so
I want to put a plug in. The Open Compute group is doing a 1-hour tutorial at Interpack in about 2 weeks. Is Interpack in 2 weeks?
Okay. I don't remember the schedule offhand, but okay.
Yeah, but yeah, so if you're interested, please register for that. There's a bunch of projects and the ODSA as well.
Okay. Okay. I've just launched a poll, so if people could take a minute and give Bapi some feedback. Okay. So actually, this probably relate one last question, and then we'll. So this was specifically about how we can motivate young engineers to contribute to open source efforts like this, but maybe you want to address it more generally. How do you get companies to allocate resources and motivate people? I mean, some companies, they assign people who it's their job to work on, and other companies, people just sort of volunteer. So how does that function as an ecosystem?
That is a real issue. I mean, we've been fortunate in having people support this consistently. It's been, I'd say, a mixture of a mixture of aligning with where the corporation is going and some degree of volunteering. So it has been, we've had people, I mean, I've transitioned companies and my new company has been kind enough to let me continue doing this. So the best formula I can see is it does require some degree of volunteering from the person above and beyond their job. But typically the reason I believe we have traction is this seems to line up with one potential next step for quite a few semi vendors. In terms of, we've seen a solid uptick in the number of people. So it is a combination of aligning with where the roadmap may be going, but with fairly dedicated volunteers who put in a lot of work above and beyond what just the company needs. So there's some sense, it took us a few months, but there's some sense that every company is getting a lot more than they're putting in when you look at the specs and the clarity that's being developed. So that's really helped us in some way.
Yeah. And anything in particular that can attract the younger engineers?
Oh, always machine learning and inferencing, right? I mean, that's really that's the biggest market for the option for chiplet-based designs, just because you can tile them, you can scale them. So in some sense, what you're doing is, but I mean, really, what we looked at was, you're basically 20% of a chip is brand new logic, or 25% of the IP, and you're spending a bunch of cycles doing the rest of it. And what this is trying to give you that harness. And this seems to be really, where machine learning and inferencing and video, all of these chips are on a much tighter turnaround time. In my mind, for those applications, you're looking at an ability to put out products really quickly at the edge or in the data center. Fundamentally, the idea is that your investment in going to product goes down.
Got it. Okay. Thank you, Bapi. Let's see. I want to let everybody a reminder that the upcoming Semiconductor Industry Speaker Series we have through the end of the year. We will post registration links on the MEPTEC.org website and send out emails. Please join us, but please take a moment to mark your calendar for October 28th, November 11th, November 25th, December 9th, and December 23rd. And with that, I will wish everyone a good day, and I thank you for joining us.